All right, welcome back, everybody. In this video, we're continuing with our discussion of section 3.4 on graphs of polynomials. Just a few moments ago, we were taking a look at the behavior of a graph near a zero. And what we'd come to the conclusion of is this. If you have a C is a zero-sum polynomial function, f, then there's going to be a multiplicity associated with C, which is how many times x minus C occurs in a factorization. So it's going to be, if you factor f, you'll have x minus c raised to the m power. If m is an even number, then the graph will just kind of bounce off the x-axis where the intercept occurs. If it's odd, then the graph will just kind of cross at its x-intercept. It could cross from above to below or below to above. That would take more work, but it's going to cross if it's odd multiplicity, and it'll just bounce off if it's even multiplicity. Okay. All right, so what we want to look at next is kind of to review end behavior a little bit. So let's see that. So we had discussed before how end behavior for a polynomial is dictated by what the leading coefficient is and what the degree is. If the degree is even, then we know the two ends both do the same thing. That is, they'll either both go up or they'll both go down. If it's got even degree, okay? If it's even degree, it's both up or both down. If it is odd degree, then you'll have one down and one up, or the left up and the right down, if it is of odd degree. When it's even degree, if a leading coefficient is positive, it's up, like x squared, y equal x squared. And then if it is negative leading coefficient, then both ends will be down, okay? When it's odd degree, a positive leading coefficient will be positive on the right side and negative down. For a negative leading coefficient, it's going to be ultimately decreasing. So left end up, right end down. Okay. So let's have a look at a couple of examples. Okay. So we just want to describe the end behavior. So here for this function f, the degree is even, okay? So the two ends are going to do the same thing. And since this is negative, sorry, that's disappearing, that's even, that's negative. Okay. So that means that overall it's going to look like that. Again, we won't know right now what's going to happen in the middle, but the two ends are that it's going to go down. How you would write this in arrow notation is you could say as x approaches positive infinity or x approaches negative infinity, f of x will go towards negative infinity. Okay, let's try that again. Here, this is odd. Okay, that's odd. So that means that the two ends will do two different things, one up, one down. The leading coefficient's positive, so that means it's going to be right end up, left end down, where we don't know what's happening in between. So as x approaches negative infinity, f of x approaches negative infinity. The function values are going down when the x's are going down. As x approaches positive infinity, f of x also approaches positive infinity. Okay. This one takes a little bit more care just because the f is factored. So we have to really think about what that leading term is going to look like. And neither you nor I want to actually multiply this thing out. So instead, we want to just think about it. So 4 minus x squared, if we multiply that out, if we did, and that's a big if because we're not going to, but if we multiply this out, this would start off x squared plus a bunch of stuff. Okay. This part, the 2x plus 3 to the 4th power, if we multiply all of that out, we're going to end up with a 16x to the 4th power plus a bunch of other stuff. When we multiply that together, we're going to end up with a 16x to the 6th term plus some other stuff. So this one, the exponent's even, so the two ends will do the same thing, leading coefficient positive, and so both ends will be up. So as x approaches negative infinity or x approaches positive infinity, f of x will approach positive infinity. Okay, by the way, you may see this written like this: as the absolute value of x approaches positive infinity, f of x approaches positive infinity. Saying the absolute value of x approaches infinity is just a way to capture both the left and right side. Okay, last one of these, negative 1/4 x cubed plus a bunch of other stuff. As we know, all these other things don't affect what the end behavior is like. It all boils down to the degree and the leading coefficient. So this one has degree 3, which is odd. Okay, so that's odd. And the leading coefficient is negative. Okay, so taking a look at the graph, if there, or the table, if there's a negative leading coefficient and we have odd degree, which we do, then the graph will look like this: left end up, right end down. Okay, so as x approaches negative infinity, f of x will approach positive infinity. And as x approaches positive infinity, f of x will approach negative infinity. All right, so that was just a quick kind of review of end behavior for polynomials. Okay, now we want to kind of remember how turning points go. So a turning point on a graph is a point on the graph where the graph changes from increasing to decreasing or decreasing to increasing. So as shown in the picture here, as you look left to right, is the graph going down or up? Pretend that we're drawing this thing from left to right, and you can neglect those arrowheads on the ends. If you look left to right, if you draw from left to right, it goes down, then it goes up, then down, then up. Okay, the places where it switches from direction, where it stops going down and starts going up, or conversely, those are going to be turning points. We also saw them described as local maximum or minimum points. Okay. A polynomial of degree n is going to have at most one less than that turning points. And we saw that before. A linear function, which is like f of x equals mx plus b, that has degree 1. 1 minus 1 is 0, no turning points. A quadratic has degree 2, and so that will be at most 2 minus 1 is 1. It's going to have one turning point. Okay, the number of turning points is always one less than whatever the at most one less than whatever the degree is. Okay, moving along. We could put together some of this stuff to help us produce the graphs of polynomial functions. So that's what we're going to do right here. So taking a look at this, we want to sketch the graph of this polynomial function. It's x minus 3, x plus 2. So this being kind of our first one, let me just draw the axes. And let's think about first placing the intercepts. I like to do the x-intercepts first. Using that box with the 4 statements in it, I can identify from the factors where the zeros will be. X is a factor, so p of 0 will have to be 0. So that means that there is an intercept right at 0. Okay, and then also we'll have one at 3 and one at negative 2. So let me make some tick marks for this. Okay, so then we'll have a 0 at 3 and 1 at negative 2. Okay, we should also locate where the y-intercept is. So p of 0 was 0, right? So we knew that. So the y-intercept is done. All right, so now we want to think about what the end behavior is like. Okay, so degree. If we multiply this thing out, it will be degree 3. Right? Its leading coefficient is going to be 1. It'll start off x cubed plus some other stuff. Okay, So since this is going to be x cubed plus, and then I don't care what comes after, this is odd degree. So the two ends will do two different things. And since the leading coefficient is 1, which is positive, it will be right end up, left end down. Okay, so now for the next part, we have to use the piece about the behavior of a graph near its zeros to know what to do. That is right here. Should I make the graph come up like this, or maybe it should turn around and come back, right? We have to know the answer to that question. And again, what dictates that is the multiplicity of the zeros. So looking back at our factored form, that 0 came from -2. That has multiplicity 1, right? 1, 1. All these zeros have multiplicity 1. So that means the graph is going to cross everywhere, okay? So the graph is going to look basically like that. How tall, by the way, how tall these bumps are, that we would need to do more work to figure out, okay? We need to plot some more points. In this type of sketch, we're mostly just focused on what the end behavior of the graph is going to be like and what the behavior of this graph near the zeros is going to be like. So we know that the graph will have its left end down, right end up, and it's going to cross at all three of its x-intercepts. Okay, so let's try that again 2 more times, okay? And read the whole directions. It says graph the polynomial functions. We're going to note the x and y intercepts, multiplicity, and end behavior. So we'll have all that on our graph. Okay, so here we'll do 42. This one has x plus 3 squared and x minus 2. So this one has a 0 at -3 and at 2. So there's -3. We'll have to go out to 2 as well. Okay, so there's that. So x-intercepts, there will be 1 at -3 and 1 at 2. Let me go ahead and put on the y-intercept while we're here, because this time the graph doesn't pass through the origin. So f of 0, okay, f of 0, 0 plus 3 is 3, 3 squared is 9. 9 times -2, -18. So it'll be down here someplace. We'll pretend that we have much different axis scaling there so you can see it on there. Okay, end behavior. So for this one, it's going to again be degree 3. The x plus 3 squared part would give us an x squared term when we multiply it out. We'll multiply it by 1 more x, so it'll be x cubed. Leading coefficient is again positive, and so right end up, left end down. Okay, so now if you think about it, with the y-intercept where it is, there's only one way that this can finish. I know that it's going to have to pass, the graph will have to pass through this point down here, but so I know that the graph will have to bounce off at -3. It can't go up and come down again, right? Why? Because then it would have another 0, right? If the graph is going to come up, right, into quadrant 2 here, it's going to have to turn around and come back down sometime to get this point on the negative y-axis. And we already have accounted for all the intercepts, and so no, that can't happen. And so it's going to have to be like that. Additionally, at x minus 2 squared, we know that this one has, I've got that backwards. It should cross at, I'm looking at the wrong one. Sorry, I was looking at 45. At -3, that had even multiplicity. -3, that one has even multiplicity, so it bounces off. And at +2, it has odd multiplicity, so it crosses through. Okay, so then let me go ahead and label some things. We'll put the intercepts on there, the xy coordinates of the intercepts. The multiplicity, we'd observe that, and the end behavior is shown. Okay, so now let's try 47 next. This one actually is going to have degree 3 again. I don't want to do another one that has degree 3. So let's do one that has, they all have degree 3. That one's 5. Let's do one with like 5. Okay, at least 44 has degree 5. Okay, so this one, 44 has degree 5, and it has zeros at 1 and -3. Okay, this one might be boring again. Let's see. So at 1, it will have a 0. And at -3, it will have a 0. The degree of the leading coefficient is 5, right? The sum of these powers is 3 plus 2 is 5, right? So there's going to be an x to the 5th term. Leading coefficient's positive, so it will be right end up, left end down. Okay, for the y-intercept, h of 0 is going to be -1 times 9, right? So -9. Then at 1, it has odd multiplicities, so it has to cross through. And at -3, it has even multiplicities, so it has to bounce off. So again, exactly how the curvature looks on these is going to vary, but we're interested mostly in the behavior of the graph at its intercepts. Okay, and the end behavior. So it looks like all of these, that's kind of poor. All of these had this odd degree. So let me make one up that has even degree for us to do, because these all had odd degree, which is kind of weird. All right, so g of x, let's go with x minus 4 squared, x minus 3, and x minus 2 cubed. Okay, that will have degree 6, so that'll be fun. Okay, so let's get some axes. This one will have intercepts at 4, 3, and 2. Let me make one of those negative. Let's go with -2. So -2, +3, and +4. Okay, so there is a 0 at 4, a 0 at -2, and a 0 at 3. Okay, there are 3 x-intercepts. The sum of these powers, 2, 1, and 3, is 6. So if you multiplied all this out, which you don't need to do, and it's kind of a waste of time for something like this, if you multiply all this out, it's going to start off x to the 6th, and then you're going to have like these 6 other terms, none of which are relevant for this. But the leading coefficient is going to be a 1, which is positive, and so both ends do the same thing because it's even, and then they both go up because that leading coefficient is positive. So our end behavior will look something like this. For the behavior near the zeros, I know at -2, that had an odd exponent, so it will have to cross through. Okay, and then the next 0 is at 3, which has an odd exponent. So again, it's going to cross through. And then it has to turn around and come back, right? It's going to have to link up against this one at 4, which has even multiplicity, and so it's going to have to bounce off there. All right, so then we can be more careful about where the y-intercept goes, and again, how tall these bumps are, but we don't need to for this type of example. All right, so we focused in this last couple of examples on how to produce the graph of a polynomial given its factored form. In the next video, we'll look at how to create a polynomial given certain requirements. So in the meantime, let me know if you have any questions, and have a great day.